Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, I want to start writing code to implement our BST. And as I mentioned previously, we're going to do this so that we create a map. And as we've done previously when we implement things, in the case of our list, we implemented it and had it extend a buffer. In this case, I want to extend Scala's mutable map. And the reason for the mutable one is because this tree happens to be mutable. In the videos, that's all we're going to write. The textbook actually goes into how you could write an immutable version of this, and it's worth looking into how to do that. As it describes up here, there are 4 methods we have to write, and we can see them down here. There are 4 abstract members. If we implement these 4, we will get everything else for free. So I want to create a new class. We'll call it a BST map. We'll have it implement a mutable map, and we'll start writing these 4 methods in here. In fact, why don't I go ahead and copy that text, and we can pull up Eclipse, and inside of ADT we'll make a new Scala class called a BST map. Now, one thing you'll note from the API is that the map type takes 2 type parameters. The first one is the key, and the second one is the value. I'm not going to use A and B. I know that is something of the standard in Scala. I'm going to deviate a little bit and use K and V because those type names have meaning to me. K for key, V for value. Extends mutable dot map of K comma V, import Scala collection mutable. Okay, and now this should be unhappy. It tells me that I need my 4 methods, so we hit paste in here. Actually, it's almost not worth it. Def def Okay, see if that will space out for me. Make sure that the plus equals and the minus equals end in this. Because I decided to change my names here, I will have to change from A and B to K and V. Take a key, get back an option of a value, and an iterator over tuples of K and V. Okay, so what do we need to do here? Well, okay, so let's make it so that this compiles, even if it's not necessarily all that happy with compiling. And yep, okay, so the iterator needs def next equals, just to make it so that it compiles, def as next equals false. Yay, we have a tree. Okay, so we're making this using a binary search tree, which means that we need to, just like if I were writing something with a linked list, one of the first things I need to do is define my node type. So I'm going to make a node, class node, and what do I store inside of my node? Well, every node needs a key of type K and a value of type V, and then it also needs a left and a right, both of which are nodes. I haven't made these vals or vars yet. Because this happens to be a mutable tree, I'm actually going to make everything vars because, well, as you'll see, we're going to need that. I'm trying to think, I might actually want to might be nice to have an update method in here, and we're going to get the apply by default. Does the API, I guess their map probably does not have, does it have an update for me? Yes, it does. Wow, we're going to get that for free if we write this. It says it adds a new one to map. Interesting. I wonder how they're writing that based upon the things that we have here. Let's go back down and look at that. Make sure it returns unit, so it's supposed to just do a mutation. That's quite interesting. As it is, we'll go ahead and we'll work on writing these. So how do we write this? Well, we have our node. One other thing that we need, private, and this has to be a var, root is a node, and it's going to start off as null. So we start off having nothing there. We could write the plus equals first. Turns out get is probably the easiest one to write, and as I often tell my students, I like to start off with the easy ones. So how do we write get? If we picture our BST, we've been passed a key and we're supposed to give an option of a value. So for example, if I were passed in the key of 6, I would look here and say 6 is greater than 5, so I would come over here. 6 is less than 7, and then I would come to here. I found the 6, so I would return some of the value that's attached to 6. On the other hand, if I were sent to look for a 9, it's greater than 5, greater than 7, greater than 8, but 8 has no right child, and so then I would return a none. Okay, so that's a nice description of what I want to do. So the first thing I need to be able to say is if well, okay, I'll type this in. Technically, I actually want to say if the key matches our thing. Let's go ahead. Var rover equals root. If you've been watching the videos, you know that I like to use this variable name called rover to represent something that moves through a linked list, or in this case, BST. While rover is not equal to null, and rover dot key is not equal to key. What should I do? Well, I need to check. If rover.key is less than key, then rover equals rover dot. Let's flip this around. If the key I'm searching for is less than that, then we go to the left. Else rover equals rover dot right. I could actually write this in a more Scala way. Rover equals, whoops, took off one too many characters. Like that better. But it still has an error. It has an error because it says you're not allowed to do a less than between these, remember, these things called k. We don't have there's no constraints upon type k. We could make it so that k has to be ordered, but as we've seen previously, at least my preference is to pass in a comparator. So I'm going to pass in a comparator here. Now, a lot of times for many of our functions we would pass in an LT, like for a priority queue we could pass in just LT, which tells you whether it's on it's less than. I can't do that here. I need to pass in a full comparator. And so a comparator is something that takes two values, does a comparison, and returns an int. And that int will be 0 if they are equal to one another, and negative if the first one is less, and positive if the first one is greater. Why do I need to do this? Well, because in this case I'm not just checking for the less than, I'm also checking for equality here. Okay, so this would need to turn into comp. The problem is, so if I don't use the comp here, this is a check for identity, which is not what I want. So if that is not equal to 0, And then this would change into if comp of key comma rover dot key is less than 0. Okay. And now we can say if rover is null, in other words, we went off the bottom of the tree, then we return none, because that was one of our breaking conditions. The other breaking condition was that they were equal, in which case we return sum of rover dot not data value. Okay. Technically this code works. I am not perfectly happy with this code. I'm actually going to make it a little bit uglier because I am unhappy with my library code calling comp twice. In general, there's this idea you shouldn't optimize until you need to, but in the case of this library code, I don't know what comparator they're going to pass me. And if these things are like integers or doubles, the comparison function is going to be really fast, and it really doesn't matter. However, if this was a simple case like strings, for example, can be slower comparisons, but there are other types of data structures where the comparison could actually be really costly, and it would be beneficial to do it as few times as possible. So I am going to make the code kind of a little less clean by doing this. Okay. And this becomes C. We'll have to, I should have kept the not equal to 0. And that way this also is C here, so that's remembered. And the next time through I have to do C equals comp of rover dot key comma. And just switch that around because that is what I've used for this one. So I compare the key that we're looking for to the key of our rover. Okay, this now is technically only going to call comp once every time through. I still have a problem with this, and that is the fact that when the way I had this written before, this check right here for rover not equal to null was actually guarding both of my places where I did rover.key. Now it's not. And so if rover is null and I try to do rover.key, I have a null pointer exception. So I only want to do this if rover is not equal to null, then I do that, else 0. And I actually need to do the same thing here too. If rover is not equal to null, I do that, else 0. Okay, so now we have a version of our get. It only calls the comparison once each time through, and we have started writing our map. We'll come back in the next video and we will add more functions to our map.